Oftentimes it is very important to, it is useful to look at things in reciprocal space. So far we have been looking at the direct space, right. You have atoms, it is a direct space, right. That is so how do we construct a reciprocal space? As name suggests, it is a reciprocal space, right. So for an example, so this is direct space on your left direct space, right. This is reciprocal, okay. So let us see direct space, you know, A1, A2, A3, 3 crystallographic axes, clear. I mean we are not plotting A3, assume A3 comes out of the screen board. So you have A1, A2 and these are the planes, right. 110 will have one intercept with one A1, one intercept with A2 and 0. Basically it is a reciprocal, because it is not cutting the A3, right. So 1 1 infinity, you reverse it, you get 1 1 0, that is what it tells you, right. Similarly 2 1 0, right, these are the Miller indices, right. So we can define this reciprocal space as this way. So we define, okay, you already know now A1, A2, A3 vectors in direct space, okay. We can say that, okay, the B1 vector in reciprocal space is A2 cross A3 over A1 dot A2 cross A3. That immediately tells you that then B1 should be perpendicular to A2 and A3, right, because B1, your denominator is scalar, numerator you have A2 cross A3. That tells you that your B1 vector will be perpendicular to both A2 and A3. So how do we plot now B1? So you know A2 is this direction, right, and A3 will be out, right. So you can get the A2 cross A3 will be B1. So B1 will be in this direction, it is clear. Similarly B2, how do you write B2 in a reciprocal space is equal to A3 cross A1 over A1 dot A2 cross A3. So A3 cross A1 means it is perpendicular to A3 and A1, A3 and A1. So see A3 and A1, if you do that cross you will get B2, right, A3 cross A1. Similarly B3 can be written as A1 cross A2 over this. So you find B3 will be A1 cross A2, now it will come out, right. So now you understand how this is in the reciprocal space. What is the benefit of reciprocal space is it maps all direct space planes onto one single point, that is the advantage. So in this case we want to map all 110 planes. What we can do, this is the point in reciprocal space which represents all the planes corresponding to 110, right. So now you got the B1, B2, now see, you see here it is 200, this will be 300, this will be 400. Similarly if you go up 010, 020, 030, 040, right. Now this one is 110. Similarly here it is 210, right, and this distance from origin of reciprocal space to the point is half of your interplanar spacing. We will come back to it. Interplanar spacing, in direct space you have planes, there will be some distance between these planes, right, that is called interplanar spacing, it is often called DHKL. HKL is plane, DHKL means spacing between these planes. So this vector, the length will be 1 over DHKL, that is why it is called reciprocal. So things here are in reciprocal. So here you have every distance is in angstrom for an example, right, A is 4 angstrom, right, here you have angstrom inverse. We are talking about reciprocal space, okay. Also notice that a plane, so this is the 110, right, and you have 110 here, usually this vector will be perpendicular to the plane. So you see this vector is perpendicular to this plane, similarly this will be perpendicular to this, right. So now what is the advantage? You can map the planes to a point. So this is the point 110, it tells you all about 110 planes. And also there is a periodicity, we will come back to it later, but just wanted to introduce this concept. Why do we do this? Because it is sometimes easy to visualize things, and also it simplifies. So reciprocal space maps all direct space planes onto single point, that is the beauty. And also the symmetry is also preserved in reciprocal space. Now same thing if we apply to different system. So here we had perpendicular axes. Now here we are talking about, suppose A1 is in this direction, right, and A2 is in this direction. In direct space we are talking about, A3 is in this direction, right. Now you have to construct the reciprocal space, you have to go back to the principle. So B1 will be A2 cross A3. Now see, A2 is in this direction, A3 is in this, A3 is perpendicular. So what will be the B1? B1 will be A2 cross A3. So B1 will be perpendicular to both A2 and A3. You only way to get it when it is this way. It's clear? Because A2, it has to be perpendicular to A2, also it has to be perpendicular to A3. So the B1 direction is this. B2 should be perpendicular to both A3 and A1. Now A3 is again coming out of the slide, and A1 is this direction. So it has to be perpendicular, that means this is the direction, right. It has to be perpendicular to both A1 and A3. So see the difference, right. Now once you have constructed this, now you can put the points here, right. So you see it will be 100, this is 200, 300, right, because we are talking about B1, again this is like a new system, new space, 400. Along this axis what will be 010, 020, 030, right, 040. Now this point will be, now we are talking about, suppose this plane 110 will be here. 110 means on B1 it is 1, and then you have to come this way, right. So this is your 110, this is your 120, because 120 means along the B1 it will have 1 intercept, and along the B2 it will have 2, right. So how do you get here? You traverse along first B1 1, then you go parallel to B2, right, parallel to, so that is how you get here 120. 110 you just stop here, 110, come down on B1, then go parallel to B2. So this is, so basically it translates all the planes to single point. So its advantages, right. Okay, now we will look into symmetry. So one of the repetition, like we are talking about again crystals where you have a repetition, right. So one of the repetition is lattice translation, you simply translate the lattice, okay. What we saw here, right, you translate this lattice in this direction, right, that gives you periodicity. So one type of repetition is lattice translation. The symmetry is the second type of repetition, right, required to define the periodicity of 3D assemblies of atoms, ions and molecules. What are we talking about? The symmetry, right. So various symmetry operators change the orientation. When you apply these symmetry operators, change the orientation of the repeated features or motifs which populate a lattice. What do we mean by that? So the symmetry, here we are looking at the symmetry element of a cube. You have a cube, now you define, you say okay, there is a, it is a reflection symmetry. Reflection means your A1 will become A2, that is one type of symmetry, clear, that is a reflection. Now about the rotation, same cube, if you rotate about this axis, right. So we are talking about different folds, right. Fold means 4-fold symmetry, means if you rotate your cube by 90 degree, it will become self coincidence, brings it to self coincidence, means there is no, so your after 90 degree rotation your A1 point becomes A2, right. Similarly, A2 becomes A3, that is this symmetry, 4-fold. 4 is coming from 360 over 4, 90 degree. If you rotate 90 degree, 90 degree, 90 degree, it will, you will not be able to distinguish, clear, that is called 4-fold. Also it has 3-fold symmetry, okay, 3-fold symmetry along this. 3-fold means you have to rotate it by 120 degree, 360 over 3 is 120. If you rotate along about this axis by 120 degree, what will happen, your A1 becomes A2, that is another symmetry operation. Now 2-fold symmetry, right, this is 2-fold. Now about this axis if you rotate 2 by 180 degree, 2-fold means 360 by 2, 180 degree. You can try that, have a cube and you can visualize it. So these are the rotation axes. Also there is a symmetry operation called inversion center. So you can see that A1 becomes A2, this is a center inverted, right, this is the inversion center, inversion, right. This is a rotation inversion, when you rotate, so suppose in this case there is a 4-fold rotation, A1 becomes A2 which we saw earlier, then there is a inversion, this A1 dash, sorry, A1 becomes A1 dash, then A1 dash becomes A2, combination of rotation and inversion. So these are the symmetry elements. You can have this kind of arrangement in system, that is what we will again come back to. So a body has n-fold, this is clear, right, okay. Again these symmetry operators we are talking about, right, these symmetry operators. So now, so the different symmetry operations acting through a point are termed point groups, okay. Now in this plot what do you see, these are the symmetry operators for crystallography, the point group designation are in the quotation. So this is 1-fold axis. 1-fold axis means you have to rotate it by 360 degree, then only it will come to self coincidence, clear. In this case B has 2-fold axis. 2-fold means if you rotate it by 180 degree, right, then this will become this will become that, clear. This one has 3-fold symmetry. 3-fold means you have to rotate it by 120 degree. You can see that these angles are 120 degrees. This has 4-fold symmetry, right. This one has 6-fold, 2, 3, 4, 5, 6. Now come back to F. What is F? Mirror plane M. It is just mirror image, right. This one is M, right. Now this one has, this is mirror plus 2-fold axis. So you see mirror and also 2-fold axis. 2-fold means you rotate 180 degree, you will get the same. Is it clear? Here you have mirror plus 4-fold. So these are the operations you can do, right, symmetry operate. So in 3 dimension the number of point groups is 32, okay. So these are the different symmetry operations acting through a point, right. Okay, we will come back to it, but before that let us look at the crystal systems, right. How many crystal systems are there, right, we are talking about the crystals, right. So 7 crystal systems exist, right, cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, triclinic. Again we will come back to these things. See how did we define lattice ABC, alpha, beta, gamma. ABC is the length along ABC axis and alpha, beta, gamma are the interaxial angles. So for example cube has 3 equal axes and at right angles. So ABC equals, A is equal to B equal to C, alpha equals to beta equals to gamma equals to 90 degree. That defines a cubic system. right. And here also you see Bragg lattices. Total are, so we have 7 crystal systems and 14 Bragg lattices, right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 Bragg lattice, right. So, in cube what you can have a simple cubic when you have this arrangement, and you can have a body centered cubic, body center, there is a atom at the center, and you can have a face centered when you have atom each face, right. So, a simple cubic is called P, I, F, these are just lattice symbols. Similar thing you can do for tetragonal. Tetragonal is you have A equals to B but not equal to C, right. You can go over it, but these are just so that defines the crystal system. It can have body centered tetragonal, right. Similarly, orthorhombic is equal to is A where all 3 sides are not equal, okay. A is not equal to B, is not equal to C. So, you can look at this, it has all B, P, I, C, F, simple, body centered, base centered, and it has the base centered also. Base centered means, yeah, this one, right, atoms in the base. Okay, it's hexagonal, right. Hexagonal has A equals to B, right. AA you see here is not equal to C, C is different, right, and alpha equals to beta equals to 90, right. 2 angles are 90 and 1 angle is 120 degrees. That is what defines these crystal systems. So, 7 crystal systems and 14 Bragg lattices. So, triclinic has no sides are equal, A is all sides are different and also angles are not equal. So, you must be wondering, like simple tetragonal, right, why we do not have a suppose base centered, like you have it here, right, in this case, but not in this case, right. You can think about it. So, why we do not have base centered tetragonal, why we have only simple and body centered, that is the question. The question clear? In tetragonal we have only simple and body centered, why not base centered for an example. See, that is what you have to check. So, we are talking about this, right. Now, you have, so suppose you have another unit cell here, right. So, basically what I am saying, you can this is nothing but your cubic, like sorry, simple tetragonal. So, that is not unique, that is the point, this is not unique, right. If you think about this, this is your simple tetragonal. These are the unique Bragg lattices you have, okay. Okay. Quickly over interplanar spacing, we will talk about these concepts. These are different things related to crystallography which we will use, that is why we are going over these things. So, interplanar spacing, we are talking about the spacing between the planes. So, here the spacing between the, in case of cubic system, when you have cubic system, right, now you know that there are 7 different systems. Cubic system, the interplanar spacing, the relationship is this, 1 over d O square is equal to h square plus k square plus l square over a square. So, if you know h k l, suppose you know the plane 1 0 0, you can calculate the, right, this is 1 over a square. So, your d is equal to a in this case, right. That makes sense, you know, you have a cubic system, we are talking about this plane, this is length a, right. So, your interplanar spacing, we are talking about these planes, right, this is 1 0 0 is a. Same thing you can do for tetragonal. Similarly, there are different expressions for other system. Okay.